electrons. Sulfur has 6. Oxygen has 6. There's 2 of them. We need 18 electrons. Sulfur will be our center. We'll drop our oxygen somewhere on the outside. Okay? And this is actually going to double well for a different question that was sort of asked in the tutoring center. I now place electrons. Where do I place electrons? Around the most electronegative element, which in this case will be our oxygen. 2, 4, 6, 8. Why do I place 8, not 6? Octet rule. That's why we have the octet rule. We can move to our other oxygen. 2, 4, 6, 8. We have another octet.
Question.
Yep.
So the book says you have to start on the very right and go clockwise. Do you care about that or not?
It's an utter nonsense rule. Yeah. Okay. Where you should start placing electrons, first and foremost, is on your most electronegative element. Okay. And so why is the book's rule irrelevant? Why should we not start on the very right? What atom is on the very right in this black drawing?
It just says very right of any particular element.
Okay, of any particular element. Okay, so that's a slightly different system. Why should I start placing electrons? Because when we talk about placing electrons, it is rather arbitrary. But if I want to place electrons on that oxygen, why should I place them on the far right as opposed to anywhere else? Is there any difference about this space than this space versus this space versus this space? Well, the red one's circled. Red versus blue, there must be a difference there. What's the difference there? I know I need to make a bond. Okay? So saying always start on the right or always start on the left is completely arbitrary. Okay? Depending on what your structure is, and this becomes more relevant in organic chemistry, there is no up, down, left, or right. It doesn't exist. The up, down, left, right that we're used to is because we're in a world centered on gravity. There is no gravity in your paper. And even then, your paper is a two-dimensional representation of a three-dimensional object that equally is not really experiencing gravity. So putting arbitrary locations is nonsense. So 2, 4, 6, 8. How many electrons have we placed? 16. So what do we need to do? 2 more electrons. Where do they go? They have to go on the sulfur. Why can't I place them on an oxygen? They already have their octet satisfied. Everywhere I have a pair of electrons between atoms, I can turn into a line to represent that bond. Am I done? No? What's wrong? Sulfur's missing its octet. So to satisfy its octet, what do I need to do? I need to move, a pair of electrons from an oxygen to the space between sulfur and oxygen. Did I have to move the lone pair on the oxygen to the right? Nope. I could have moved the lone pair from the oxygen on the left. Right? So both of those are potential options. Do I have my octet? We go back to our colored one. Yeah, all my atoms have their octet, which then means which of these is my answer? Both. Neither one is correct on its own. You would need both to be correct. Okay? You slowly build your way to get to the answer. Kind of, sort of? Does that help you out, Marcy? We good with that one? Do you want to do the fluorine one too or something else? There's a fluorine one and I see a hand.
Can you just let me a specific example of like
Yes, I can give a specific example for the octet rule not applying. Let me do the fluorine first, and then we'll go to that one. So I'm going to erase everything, because now we're going to shift focus to our fluorine. So F2, fluorine has how many valence electrons? Fluorine has how many valence electrons? 7. There's 2 of them, which gets me 14. So I appreciate the 14. You're just jumping the gun a little bit. Put my fluorine. Okay, I can start placing electrons around the most electronegative. It's the same element, so it doesn't really matter. Again, where do I want to preference? I'll preference the space between the atoms, but it ultimately doesn't matter. 2, 4, 6, 8. I've done an octet, so now I can move to the next one. 10, 12, 14. We have 14 electrons drawn, which now means can now go through to draw bonds, pairs of electrons between atoms. Do each of my atoms have an octet? Yep, which then means we're done. That's it. Right? And a lot of the rules that you see online come from this Lego model kind of type build for structures. Simple structures work. Right? But what they do is remove so much content knowledge that it destroys your ability to do anything correctly in the future. So the Lego build model should be left for elementary school, and no one should be talking about that ever again. Right? After that, you're more intelligent people. You deserve to see a proper bonding system. Okay? Kind of makes sense? Cool. Do we have exceptions to the octet rule? Yeah. To that end, we'll give you 2 examples. Draw the Lewis structure for CH4 and draw the Lewis structure for BH3. Spend some time, get those drawn out. Carbon has how many valence electrons? 4. For those people that aren't shouting 4, that's okay. For the people that shouted 4, hold your horses for a second. Those people that didn't shout 4, where do we find the valence electrons quickly and easily? That goes to the periodic table. It's the column name. So if you look on top of where carbon is located, that entire family or group, that vertical column, that name up top is IV. And if we don't know our Roman numerals, okay, that becomes a little bit more challenging, but IV is 4. Okay, you can also look at the 14. Ignore the 1. It's 4. It helps. Okay? And if you look at the other one, well, what about 13, 15, 16, 17, 18? Same deal. Ignore the 1. And you've got your valence electrons for each of those columns. Kind of makes sense for anybody who didn't shout? Okay. Hydrogen has how many valence? 1. There's 4 of them. My total is 8. Okay. Carbon, and then I'm going to draw something that's going to be a little bit more challenging for me. I apologize. Hydrogen, hydrogen, hydrogen. Okay, and I would bet the majority of you did not draw it this way, and that's probably because you've been following too much, not necessarily too much, but been following more along the lines of my directions. Okay, for people that drew it this way, this isn't wrong to draw it this way. Okay? The whole point of how I've been telling you to go through and draw is based off of a square. You can still draw a square on this, but it looks more like a diamond. Okay? Why do we want the squares? It falls back to Lewis structure. It falls back into what we need for shape with Vesper. Okay? So if you're happy with drawing diamonds instead of squares, that's okay. You can do that. Just realize it might be a little bit trickier to wrap your brain around it, maybe. Okay? We still want to go through and place electrons. Which atom is most electronegative, carbon or hydrogen? Carbon. So we'll place our electrons around the carbon first. Again, placing in between. Okay. As we place in between, we've drawn our 8 electrons. Anywhere we have a pair of electrons between atoms, we can turn into a line, bond, 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 bond. Okay. to Eden's question. Do all atoms have an octet? Does carbon have 8 electrons around it? Yes. Does the hydrogen? No. Ooh. Does that mean I need more electrons? No. Okay, and this is a challenging one that students will oftentimes stumble on. Okay? What we're trying to do is satisfy that energy level. That's what we're referencing when we talk about octet. And we're typically looking at atoms like chlorine or boron. And if we look at chlorine and fluorine, boron, carbon, nitrogen, all of those as simple elements happen to be in row 2. And how many columns are there in row 2?
Are you counting the noble gases?
Yeah.
5. Oh no, 6, 7.
6.
Oh.
In row 2.
8.
There's 8. Row 2 starts with lithium. How about in row 3? 8. Why is it octet? That's the common bonding patterns. What we're satisfying is the entire energy levels electron configuration. Row 3 starts to throw in a little bit of a monkey wrench into it, but we're going to pretend I didn't mention that, and we'll ignore that because we won't look at those structures. Okay? Octet is the primary issue. When we get to hydrogen, how many columns are there for the first row? 2. Its octet is 2. Okay? To the point where some instructors will go through and say, well, we have an octet rule and we have a duet rule. Duet, because duet is referencing 2. Do I need an extra rule for one element? That depends. I don't think so. The other instructor that I worked with thought so. Okay? So the question that I would then ask is, do you want a separate rule? If you want a separate rule, yes, there's a duet rule for hydrogen. Okay? That's your decision. So there's an exception. Hydrogen is a huge exception to this. Okay? So let's push a little bit harder and let's move to the next one. RBH3. Sorry, can I erase that one? Yeah, good. Okay. BH3. How many valence electrons does boron have? 3. How many valence electrons does hydrogen have? 1. There's 3 of them total. 6 electrons. This should already be screaming we've got a problem, because if we're supposed to have 8 electrons around something, if I only have 6 electrons, we're going to come up short. But if we test this out and draw it out, boron's technically not more electronegative than hydrogen, but we won't stress about that. We'll place our 6 electrons. Everywhere we have a pair of electrons between atoms, we can turn into a line, and we've got a bond. We now encounter the question, does every atom have its octet? No. Okay, so what do I do? And oddly enough, your silence is the perfect answer. Nothing. There's nothing I can do. I can't put in more electrons. I can't move electrons because there's no electrons to move. I'm only allowed to move non-bonding electrons. This is my drawing. This is the Lewis structure for BH3. It's done. Okay. Does the boron have an octet? No. Is there anything I can do about it? No. So I'm stuck with it. That's the way it lies. Okay? It turns out that's actually one of the reasons why boron's chemistry is the way it is. If you take future classes, boron as a reagent shows up. And it shows up and we take advantage and we leverage this missing octet heavily to do lots of different chemistries. Okay? Does this mean boron is always missing its octet? What if I do BCl3? We'll do this one together. Boron has how many valence? Chlorine has how many valence? 7 times 3 gets me 21. 3 plus 21 is 24. I'll draw my boron. Chlorine, chlorine, chlorine. Those are chlorines, not uraniums. 2, 4, 6, 8. 2, 4, I don't know why I'm counting it as 8. This gets me 8 electrons around each of those chlorines. That gets me to 24. I've drawn in all my electrons, so now I'll go through and change things up. And draw in my lines. Does every atom have an octet? Nope. So what do? What's that? That was the advanced answer to the question, but yes. I'll move a pair of electrons from a chlorine atom into the space between a boron and a chlorine, and I'll make a double bond. Why? Why do I make the double bond? What was the problem with my structure? I didn't have an octet. So why do I need to move electrons? To make an octet. If I have the ability to do it, I do it. Okay?
It's better than not.
Yep. And that becomes kind of this weird statement. Like, do I have to? Like, why should I do that? And ultimately what it's going to fall down to is the rules. The primary rule is octet. You make octets. Okay? There are cases where you can't make octets. Like hydrogen could only ever hold 2 electrons from where it's at energy level. Okay? There are cases like BH3 where I literally don't have enough electrons to make an octet, so I can't. But if I'm given the choice to be able to do it, I do it. Okay? And then as was suggested by someone towards the back, this introduces a whole nother mess. Did I have to take the electrons from the rightmost chlorine? No, I could have taken from the left or the bottom, which then means I would have to draw all 3 to satisfy that I'm showing resonance. Hooray, resonance. Okay? And if you feel like you have a problem with resonance, you do. Okay? Everybody does. It's a challenge. It's going to show up again if you have to take 151. It'll show up again in OChem 1. Okay? And it'll show up again in OChem 2. And in all of those cases, we will keep trying to hammer it into you what the concept is of resonance and how it can be used to manipulate and change chemical reactions. At this stage, all you're trying to do is acknowledge its existence. Okay? Which again, isn't necessarily easy. Don't stress. Okay? Or don't stress a lot about it. If we look at the point breakdown, this question had 9 points. SO2 and F2. 9 points split across 2 places. Let's just say we get rid of the SO2 and we made it BCl, oops, wrong eraser, we made it BCl3. Do you think if you didn't draw a resonance, you would lose all 9 points? Okay. Hopefully you realize, no, that's not the case. There was a lot of extra thought that went into processing that. Why'd you put boron in the center? Why are chlorines on the outside? How many electrons did you put in? Did you show a double bond? All of those questions, if you're providing correct answers for, are points. And if you miss the resonance part, okay, let it go. Okay? Yeah, you'll deserve to lose a little bit more points. That's okay. It's 1. Don't freak out over 1 point. Kind of, sort of? Does that answer your question about octets? You happy with that? As happy as you can be?
Yeah.
Okay. Next question.
You put out palm coin and it's like for hydrogen, how does the 4, like the 7 times 3, and then how that happened with like the F, that line?
So, this goes back up to our formulas. So when we see BCl3, what does that mean? Okay, and this I would actually goes even further back if we reference our atomic notation. Okay, which in the lectures I call nuclear notation because it's more relevant for nuclear notation. We have a symbol for an element. We'll call that SY as our symbol. What shows up in the upper left-hand corner?
The power.
I miss left and right too. It's okay. Our upper left-hand corner is your mass number. What is mass number? Protons plus neutrons. What's in the lower left-hand corner? The atomic number. And what is the atomic number? Protons. Conveniently kind of organized in like a little mathematical expression where if you did the subtraction, you would now know the number of neutrons. That's kind of neat. Okay. What's in the upper right-hand corner now? This is our charge. How do we calculate charge? There's a couple different ways that you can go through and do it. My least favorite way, but it works, is protons minus electrons. Right? I don't like that because it's a formula to memorize as opposed to just the meaning behind it. What's in the lower right-hand corner? The amount present. This notation can be used with every single formula. So when we look at BCl3, let's delete all this. I could be going, oh, this is going to take a little bit. Let's see if I can pull this off. I could say boron 11, 5, 0, 1. Whoops, I need a little more space. Chlorine 35, 17, 0, 3. What I've just written is, for all effects, the same thing as what we've got written up here, BCl3. But what I've decided is that I don't care about the mass number or the atomic number. Why do I not care about the atomic number? Why do I not care about the amount of protons?
Because they tell us like a charge or like, I mean like anything about the electrons. Because we're trying to find the valence electrons.
Those are the ones available to make bonds.
If I tell you atomic number 50, what can you tell me? Okay, so oh, that's 50 protons. Okay, keep going. What are you doing, Brendan? But you're not thinking looking over there, and you're not thinking looking at me. You're thinking looking at the periodic table. Why are you thinking looking at the periodic table? I know, I just put you on the spot. It's okay.
Just trying to remember what I know from it and how to read it.
So you weren't potentially looking at the 50 atomic number?
I wasn't squinting some of my glasses on.
Oh, so you were looking at that? Yeah?
Finally, yeah.
Yeah, cool. And so when you knew that 50, you knew that the symbol was SN. And if you spent the time to memorize it, you would know SN was 10. If I tell you B, how many protons do you have? 5. Those two pieces of data are redundant information. Right? If it's redundant, if I'm already going to have to tell you the B, why should I show the 5? If I'm going to tell you the Cl, why should I tell you the 17? Right? Mass number. Is the mass number going to change for a chemical reaction? Much harder question for you guys to go through and answer. What particles contribute to the mass number? Protons and neutrons, which are found where? In the nucleus. Do we do any nuclear chemistry? No, why not? What is nuclear chemistry? Boom. Right? Like that's, they call it nuclear bomb because it's doing nuclear chemistry. Right? That's really dangerous. Kind of beyond, it's content-wise, it's not beyond the scope of the class. Okay? But actual playing with, yeah, we probably shouldn't play with that. Okay? Which means, do I really need to show the mass number if we're not going to worry about that changing? No, so I can delete that too. Okay? Well, the charge. Right? Should I be worried about the charge? Well, if I'm going to put together a molecule, I probably don't care about the charge on the individual atoms. I care about the charge on the overall molecule, which means I could drop this one, and then this one is going to change to not being associated with chlorine anymore. It's going to be associated with the entire molecule. And if it's neutral and going to be 0, why should I bother to write the number? Yeah, good point. Let's not write it. And if I'm going to bother to write the B, that number in the subscript is probably not a 0, because then why would I bother to write the B? So that drops off. And what do I get? I get my formula, BCl3. So what does it mean? That 3 is referencing the amount of chlorines. When we go through and look at the valence electrons, chlorine had 7 valence electrons. Why did we multiply by 3? There were 3 chlorines. Each of those chlorines is going to bring in 7 valence electrons, which is why we have to total that in. And for those of you being like, that was really roundabout, Mike, that was rude. We just reviewed like 4 major concepts for the rest of the exam. I would say that was pretty freaking awesome. Make sense? Do you feel better? Okay. Those subscripts reference the amount of the thing immediately in front of them. Okay? Which is going to immediately come back and haunt you at the end of this week when we study nomenclature. Yay! Okay? But you have to remember what they're referencing. It's the amount. Next question. Yes?
Can we go over number 21?
You're laughing. That makes me nervous.
I'm not laughing. I just need some help.
You're smiling with gusto. Did both of them go down? That was lovely. Really? Okay. More than one way. Nope, there's not more than one way. How do you take a screen capture on an iPad?
You use your Apple Pen and slide up the left corner. Or power button.
Yeah, volume button. Yeah, power button.
Yep, not that button. Volume up and power?
Yes.
You're still not going to let me do this, are you? You're, no, you're not going to let me do this. Fucking bastard. Whoops, I said that a little loud. So, to the recording, sorry, it ain't happening. You just get the audio. So, our playback on this. What are we trying to do? Knock it off. So, if we look through the information we got, we have bronze, an alloy of copper and tin, which is really just a mostly useless statement. If a bronze statue has a mass of 43.2 kilograms, so we have 43.2 kilograms of what?
Bronze.
See, this becomes the challenging part. You have to be able to pull information out of the question. Okay, and as we pull that information out, we have a number unit, we have a measurement unit, and we have a substance unit. All three components must come with your system. That should sound vaguely familiar. Okay? And if you're like, that doesn't sound familiar to me at all, that's because hopefully you're not in my lab. Because people in my lab should have read the background information and been yelled at multiple times to do so. People in other labs had better be reading the background information because it provides some useful context. What's the substance unit here? A bronze statue has a mass of 43.2 kilograms. Pause. 43.2 kilograms represents what? We could say the statue, but what's the statue made out of?
Bronze.
Bronze. And is 88.0% copper. Okay, so we go with 88.0%. Ooh, cool. You said CU. Why did you say CU and not COPPER? Because you're lazy and you didn't want to write it all out. That's awesome. Okay? We're going to push on this a little bit. This is something that I complain about with these percentages. Okay? This is a percent, but let's pull this into something that's useful because you can't enter a percent into any of your calculations. Believe it or not, you're never doing that. Okay? What you're actually doing is you're taking the percent and turning it into what it means. What does per mean? Miles? Oh my God, I can't believe I just did that. Let's try that again. MPH, miles per hour. What does that mean? Miles, per hour, right? What does per mean? This notation is useful because that notation allows us to see a clear top and bottom to our fraction. When we go back over to here, this says percent. We got the per showing up again, which means division. And it says percent. What does cents represent? 100. And we know that because if I have 1 cent, that's only useful, sort of, not in this economy, if I collect 100 of them to make $1. Okay? So when we say 88.0%, it's actually saying 88 per 100. And now my complaint. 88 what? You say copper, that's the substance. What's the measurement? Okay? And this becomes kind of a nasty question. When we talk about percents, we should be a whole hell of a lot more clear what we're referencing the percent as. Okay? When we talk about in chemistry, it's usually done in 2 different ways. Mass or volume. Why would we pick mass? Because it's a solid. Why would we pick volume? Because it's a liquid. Is copper a solid or a liquid? It's a solid, which means we want a mass unit here. Okay? Copper per what? 100 what? We're assuming grams. Why do we need grams? So that our units can cancel. This is 88 grams of copper. Okay. Percent copper. Again, this is referencing the system that it's coming from. If a bronze statue has a percent of 88.0% copper, we're saying there's 88% copper in the bronze statue. This is bronze. Okay? What is the mass of tin in the statue? Okay? This is where that first sentence can come into play. Because if I look at my given information, I've got bronze and copper. Do you see tin? No. So where does the tin come into play? Bronze equals copper and tin. So I can now set up my expression. What do I want?
Mass of tin.
Mass of tin, okay? Tin will be the symbol SN. If you don't know that, that's okay. You can get away with writing TIN. What measurement unit do you want? What's that? Grams? Do we want grams? We want kilograms. Right. We go back over here. Nick, when he was talking about that 88%, okay, said probably only loud enough for me that I wanted kilograms of copper. And I totally thought I was answering a different question, and I ignored him and wrote grams. Can I write kilograms here and have it not change any of the meaning?
As long as you put it on the bottom too.
I have to address it in both spaces. As long as I address it in both spaces, I'm okay. Because I'm now doing the exact same scalar factor to both sides of my expression. Make sense? So far, so good? Okay. So, what do I want to do?
Percentage of tin.
Okay, so you look at this saying, I want kilograms of tin. This says bronze, this says copper, and this says bronze. So it doesn't say anything about tin. So could I do something to get to my percent of tin? If I have 100% bronze, and here I might be lazy. I'm not going to be lazy. I'm going to write it out. What do I know that's going to be equal to? 88.0, whoops, percent copper plus the percent of tin. Why do I know this expression is true?
Bronze made up of copper and tin.
That very first sentence, bronze is made up of copper and tin. Okay? So I can now solve for the percent of tin. The percent of tin is going to be equal 100% bronze minus 88% copper, and this is going to give me 12% tin. Just like we did with our kilograms of copper and bronze, what else could we do? $12 kilograms of tin and 100 kilograms of bronze. Yeah? What do I want? What do I want? Kilograms of tin. Now looking at my given information, do I see anything about the kilograms of tin? As in, do you see the letters K, G, S, N? Yes. Where do you see them? Right here. So I'm going to take this given information and put it on the left side of my equality. And I want to put it in such a way that it gets as close to the right side of my equality as possible. So where should I place my kilograms of tin? Do I want it in the numerator or in the denominator? Whoever said denominator, thank you, I needed that. And that sounds sarcastic. I'm not being sarcastic at all. Look at your equality. In fact, let's ignore the kilograms of bronze. Does that look like an equality? Right? Said another way, let's say the kilograms of tin is 2. 2 equals 1 over 2. Is that a true statement? No. So what you decided to try and do was cross-multiply, which is, quite frankly, bullshit. Okay? Follow the units. I want the unit where? In the numerator, which means on this side of the equation, where does it need to be?
On top.
In the numerator, the exact same space. This is why I wear long sleeves. Do I know just the kilograms of tin? Go back to that given information. Was it just kilograms of tin? Look in this circle. Is the only thing there a number next to kilograms of tin? No, there's a line, and underneath that line I have some more stuff. Which means all of that information has to go in. This is kilograms bronze. Do I know the numbers that go with those? Yeah, they were in the given information. This is 12. This is 100. Are you making progress? Yeah, it may not seem like it because I talk slowly. Kilograms of tin, kilograms of tin. You've got the units appearing exactly where you want them to be, in the numerator on both sides. Do we have a problem? Yeah, I don't want kilograms of bronze, which means what has to happen here? I have to have the kilograms of bronze appear in the numerator. So now I can go back to my given information, and do I have the units of kilograms of bronze appearing somewhere? We ready to chase down a wrong path, or do you want the right path? Right? Okay. Kilograms of bronze. It says right here, 43.2 kilograms of bronze. Not related to anything else. Which means I can place that 43.2 right next to the kilograms of bronze. That's where it was placed in my expression. What goes in the denominator? 1. The only thing I can place there that doesn't numerically change my number or alphabetically change my measurement. Now what happens? Kilograms of bronze as a unit cancels. I can take 43.2 times 12 divided by 100 and I get my answer. That seemed to surprise me.
Yeah, that was a lot easier than what I did. Good.
You have to track your given information and process. Do you have to follow this methodology to get to the answer? Be louder with your head shake. No, you don't have to do exactly what was up here. There are some people that can process all of this calculation, I would argue, in your head, more or less. Some people can do it in their head. That's great. That's fantastic. Because they can do it in their head, where is this question showing up? In the multiple choice, where you're not required to show work. Right? Those people that are doing it in their head now are going to encounter a rude awakening in our third unit when we bring in more calculations. Because instead of having practiced a process where they're tracking the units, they're now going to have a problem where they won't have a process to track the units anymore, to figure out where all the numbers belong, and they're not going to be able to do it in their head quite as efficiently. So right now, your whole process is how do we find a process that works? I'm giving you a process that works. You can choose to use it or not at your own demise. Make sense? Track your units and move through, and you should be better off. Questions about that? Just because someone put an answer, was that the answer? Anybody actually calculate it?
Yeah.
I got 5.
5. Okay. Calculator spit out 5.184. It says 5.18. Do you have to worry about sig figs? Some people were like, yes! And there's a couple people that are saying no. Okay, for those people saying no, why do you not have to worry about sig figs? It has nothing to do with whether it asked or not. Do you see the answer, 5.184?
No.
That's how you know you're not being asked about sig figs. You will know you're being asked about sig figs because when you look at your answer choices, they will all be the same number with varying amounts of sig figs. Now it's a sig fig question. Here you're being asked to run a calculation. So what we're testing on is, do you understand how to run the calculation? They're testing different purposes. Make sense? Okay. Just because it happened to flash on me and I remembered, when building this exam, guess what I entirely forgot we talked about? Sig figs. So I don't think there's a single sig fig question in this first exam. Not positive, but I'm about 95% certain. Okay? Which means it's going to come back in the next exam. Whoops. Sorry. Or hooray. Okay, some people are hooray. That's good. Next question.
Can you please do number
23? Okay. Cool. Let's see. Did it decide to start miraculously working? Yep. No, that's, yeah. I'm pretty sure all my technology is failing because of this software. Okay. 23. Yep, this is why I wear this shirt. Oh, there it is. So what are you being asked to look at? Atomic radius. Okay. To answer this question, you would think, oh, you need to know radii. That's not at all actually what this question is asking about, which seems very counterintuitive. What this question is asking about is experimental data. Can you evaluate data given to you? That's it. It just happens to be the data is talking about radius. But particularly in a practice exam situation, what I'll get people doing is going up and looking up the radius. That's not at all the point of the question, because you're expected to do this question on your own without the internet. So how do you do that? Right, so if we're going through and looking at this, we're talking about silicon, we're talking about tin, and germanium. So I capitalize all the other ones. Silicon has the symbol. S is half right. Si tin, Sn germanium. Cool. Okay, so if we go through and look at this, radius for tin, 0.141, what did it say, nanometers? Germanium, 0.123 nanometers. How could I ever possibly understand what the radius for tin or silicon would be?
Predicting trends.
Predicting trends. So this goes back to chapter 5 and looking at trends within the periodic table. And one of those trends had to do with atomic radius. And so what we would go back and do is see what is the relationship between silicon, tin, and germanium. Okay? And I would argue, without even dealing with predicting trends, you all are freaking chemists right now. And chemists at all times have a periodic table. Which means if you're being asked anything about elements, your first go-to place is the periodic table. So let's figure out where silicon, tin, and germanium are located. And if we look at it, we'll see silicon, germanium, and tin. So this is off our periodic table, yeah? All right. Now let's backfeed some information. For the tin, we know we have a radius of 0.141. For the germanium, we have a radius of 0.123. Okay. Given the data, what's changing with our radius? Okay. I love the answer that was shouted out that hopefully everybody heard. It's getting smaller, but I'm actually going to challenge it and say I think it's getting bigger down the periodic table. Who's more relevant, me or you? You are more relevant because you're trying to figure out that question mark. So we don't care that we're going down and it gets bigger. The place I'm trying to find is above. Does that make sense? So when we're looking for these trends, be explicit in those statements so that you can call attention to it. So what we need to do is get a smaller radius. Smaller radius than the germanium. So it should be less than, how do I do that? Less? I think I did that right. 0.123. Okay? How much less than? Okay? What's the data set that we have at hand? How much did this go down? That went down by 0.02? How much would you expect the next one to go down by, being one step? 0.018 is a decent guess based off the data we got. So what can we do? That's what the data gives us. Is that the actual radius? Probably not. Actually, I have no idea. Right? But this is the information we have at hand. So with that information, we can go back and look at our answer choices and see what we've got. Right? 0.077. That's underneath. Is that a reasonable underneath? No, that looks like a really big drop. So 0.077 doesn't make any sense. How about 0.167?
It's higher.
That's getting bigger, so that also doesn't make sense. I get 0.0132. That's even bigger. That also doesn't make sense, which means A, 0.115. Based off of the data we have at hand, that's our best guess. So the answer is A. How do you reason through with the data that you have at hand to come up with a reasonable prediction? This is effectively looking at scientific method. How do we process data? And it doesn't have to be true at this point either. That's the other kind of important thing. This doesn't have to be 100% correct. It just has to be the logical flow based off of the data that we have at hand. As we learn more information, we can modify our theory. But at this point, that's all we've got.
There's over 20
Just a second. Does that make sense?
Yeah.
What did you say?
Could you go over 24, please?
Oh, you did say 24. Chemical formula CH4, NH3, H2O. Predict the formula for SI. Guess what this question is? The exact same thing that we just did. We're again looking at periodic trends and how can we predict and manipulate them. Right? So I've got CH4. Oh, when do we end? 45? I got a little time. NH3, H2O, and then I want to know about SH. Okay? So if I'm going to try and figure out something about SH, I have to know something about those compounds. Okay? So what do I know about those compounds? And if again, I'm like, well, I don't know anything about those compounds. Well, what changed? The amount of hydrogens changed for each element, right? Well, how are those elements related? Thank you, Bryn. You were the only one looking that way, so. As soon as we ask that question of how are those elements related, it's an immediate periodic table. Use the information we have at hand. And if we flip that, we're looking at CH4, NH3, H2O, we're looking at our periodic table across that line. Where is, whoops, I said S, sorry. Where is silicon?
Underneath carbon.
What do you think the formula is for silicon and hydrogen? Do we have any relationship to the NH3? No. Any relationship to H2O? No. Do we have a relationship to carbon? Yeah. They're in the same group or family. And not all families are treated equally in the grand scheme of families and all that. But typically, when you look at families, they react the same. Why do families react the same? What reacts? The valence electrons. And so why would elements within the same family react similarly? They have the exact same valence electrons back to that number at the top of the column. So if we're going to look at this, the best answer in this case is going to match the one with our CH4. We're going to look at SiH4. And there we go. I want to push on this a little bit more because I forgot to do it with the other ones. Do you see SiH3 as an answer choice? Do you see H2Si or SiH2? Yeah. All of those answers are potential ways to go through and approach this question, which is why those answer choices are present. You have to understand a little bit about what's going on within it. You can make the argument that SH makes sense. Why would SH make sense? Well, I have 4, 3, 2. What comes after 2? 1. You could also make the argument that SiH5 as a distractor makes sense because 2, 3, 4, 5. Do you understand where your patterns of those elements are located? Marcy, that was you, right?
Yeah, that was staring me right in the face now. I'm like, duh, moron.
No. The format of the question makes that very challenging to go through and see. Break the format. This is something that most people would not show any work for. When you first read the question, was it obvious to you? Right? Some people were like, yeah, shut up. Right? For the rest of you, when I changed it to write out the periodic table, did it become obvious? Oh, so you mean how things are formatted can change your ability to interpret? Yeah, so provide that formatting. That's you writing something down. That very subtle change in how that information is presented can shift it from being an entirely unknown answer to something that becomes obvious. But you have to push that formatting. You have to write it down. And if instead you decide you can do it in your head the whole time, all your head is going to do is act like a deck of cards and shuffle everything. And you're going to lose all of that formatting. Write it down. Next question.
Can you just provide a definition for quantized? Yep. Is that how you say it?
Yeah. Quantized. Here's the definition. Just work here. Quantized is discrete energy levels. Right? Stairs are quantized. You cannot exist at a half step. Right? Ramps are continuous because you can exist at any point along that ramp. But stairs, you can't exist at those half points, those half levels. You can only exist at each level. Why is that an important question? What is it referencing? What do I see?
Energy levels.
Energy levels for our electrons. Right? It's that quantized state that gets us atomic line spectrum. Okay. 26. Wow, there's just a run of questions right here, isn't there? All right. Without knowing energy differences between these, we can't predict necessarily what color any one of these necessarily is. So we are taking in some massive liberties within this. Okay? So let's start. What do we know about violet light? How do you know that's high energy?
Has a high frequency, low wavelength.
I'm just going to trust you on that. I always have a hard time with frequency and wavelength. Just memorized. Okay, high energy in comparison to what? Gamma rays? Okay. Higher in energy in comparison to, red. So if we're going to look at it, we have violet is higher in energy than indigo, blue, green,
Yellow, orange, red.
yellow. Thank you. I heard blello. I was very confused. Right? You should know that energy difference, and yes, I would recommend you memorize that. I do tend to struggle with it as well. What finally stuck with me is that when I step outside, I'm typically afraid of UV radiation, ultraviolet radiation. And so I put on sunscreen to protect me from that ultraviolet radiation. I'm protecting myself from that high energy form. Which light is closer to ultraviolet? Violet or red? Violet, it's in the name. That's what helps out. Okay, for me personally. So what we're looking at is something that's a high energy transition. So now we can look at each of these transitions and say which of those is going to be the highest energy. Five to 1 is the largest energy. That's going to produce the most purple light. Okay, which would be the most red? So we switch this up. That's purple, and that's red. Do you think I could ask a question about which one was the most green?
Yes.
Okay, if you think I can ask that, then here it is. Which one's the most green?
Would it be the 3 to 1?
I genuinely don't know, because I wouldn't ask that question. You're now sitting somewhere in the middle. Yeah, it's one of those middle ones. I don't know which middle one, it's one of them. Right? So when we're getting this question, what we're getting are the extremes. Okay? Which is important, because what you're now addressing is the content of the question, not the question itself. Which means you've now just created a possible test exam question that could show up on the exam. Which one was the most red? How else could I ask it? Which one's the highest energy? Which one's the lowest energy? Probably wouldn't do it, but I could ask which one's the highest frequency? Which one's the lowest frequency? Highest wavelength, lowest wavelength. Because all of those things are related to each other. All of those things could be tied into this exact same question. Getting all of the exact same content. And then you have to decide where my threshold for what you know and don't know becomes relevant. Okay? Frequency and wavelength, I already gave you a big clue. Okay? And if you're like, I missed that, it's probably about 40 minutes into this lecture. It was probably about 55. Go back and rewatch the lecture.
I do 32.
Hey, it started working again. I think we did this one. Is it going to break again? Nope. I wish it just stayed broken or stayed fixed. It must be one or the other. So, what's the first thing you need to be able to do? Find sodium on the periodic table. So you'd look for S, right?
No,
Oh, okay. You need to know all the symbols for your elements. So this question is not just asking, do you understand electron configuration? It's also asking, in a sneaky, backhanded way, what are the elemental symbols? Okay? So we have to look for Na. So we could go to the periodic table and we could find Na. When we talked about sodium and particular electron configurations, we said the most important point was to find its unique identifier. So its unique identifier is the game of Battleship. Where is it located? So what row is it located in? Row is left to right.
Third period.
Okay, you guys are just using terms that are just confusing the hell. I just want 3. It's in the third one. Okay? It's in the third row.
Period.
Okay? Which is technically a period. Okay? You can see how often I use that term. Okay? Which block is it in? The S block. Okay? Which column of the S block? Okay? That is going to be the most important identifier information for sodium. Okay? So 3s1 has to be very, very critical for our electron configuration. So with that context, we can now get rid of A, we can get rid of C, we can get rid of E. And we're now left with 2 other answer choices, B and D. When we're talking about the electron configuration, we want all the electrons for that individual element. Right? Every single one. Sodium has 11 electrons. If I just say 3s1, I'm only specifying the location for 1 electron. I need to specify the location for the remaining 10. What is 2 plus 2?
4.
Plus 6? 10. There's your remaining 10. That's the rest of your configuration. Okay? So your electron configuration for sodium is going to be 1s2, 2s2, 2p6, 3s1. 3s1 is going to be our critical piece of information that we absolutely must know. The rest of it is just fully saturating the rest of the orbitals. Kind of makes sense? The fill pattern behind that we've done a couple times in older videos. I would kind of push you back to those older lecture videos where we went through and looked at each single one. My clock says I got 2 minutes. Next question. No other questions?
So the short version of that, you put NE in brackets and just write 3s1.
So the short version of that, we'll talk through that. Well, I'll just mention it, kind of confirm, is that we can look at that part and acknowledge that that is just the configuration of neon. So we can use the noble gas shorthand, and we could say neon 3s1. But as we talked about before, I'm not going to test on that because I think it adds a whole nother layer of confusion that people just don't need. I would rather you actually acknowledge that last part importantly first and then just realize the rest has to fill out. If you need to deal with 151, you can worry about that shorthand. With that, we'll go ahead and call it. You're getting too antsy.